This is a short introduction to our paper, Human-Object Interaction with Vision-Language Model-Guided Relative Movement Dynamics. Human-object interaction is crucial for advancing simulation, animation, and robotics, aiming to generate long-term, physically plausible motions in 3D environments based on human instructions. Recent approaches utilize physics engines to create interactive environments where agents learn interaction skills through goal-conditioned reinforcement learning. However, many interaction tasks require carefully designed, task-specific rewards crafted by human experts, which is a highly challenging process. Moreover, these task-specific formulations necessitate separate policy networks and surround transitions. In contrast, our framework supports automated reward design and a unified interaction formulation, overcoming these limitations. In this paper, we introduce a unified, physics-based framework for human-object interaction skill learning. Our approach leverages the powerful world knowledge of vision-language models to control interactions between human and object in both static and dynamic scenarios. Moreover, we introduce a spatial-temporal bipartite diagram that allows us to model complex, dynamic human-object interactions in a very fine-grained way. RMD also helps us automatically construct a unified reward function, which is critical for training agents in reinforcement learning tasks. This makes it easier to handle a wide range of interaction scenarios without the need for task-specific rewards. Lastly, to better evaluate our performance, we present Interplay, a novel dataset containing thousands of detailed interaction plans including both static and dynamic interaction tasks. The relative movement dynamics characterizes the spatial-temporal relationships between human body parts and object parts within each subsequence. To effectively represent RMD, we employ a bipartite graph structure in which each node corresponding to a human body part is uniquely connected to a node representing an object part. Edges in this graph explicitly encode the relative movement dynamics between these connected parts. The primary workflow of our approach is detailed as follows. Initially, we employ GPT-4V as our planning module, decomposing high-level tasks into multiple subsequences based on inferred spatial-temporal relationships between humans and objects within specific contexts. The planner generates outputs structured as bipartite graphs, with nodes uniquely pairing human body parts to respective object parts. Each bipartite graph corresponds to a distinct temporal segment, within which the relative movement pattern between each paired human and object part remains consistent, before transitioning into subsequences. These planned subsequences are subsequently utilized as inputs to the control policy, which executes them sequentially. We evaluate HOI skill learning in both single-task and multitask scenarios, achieving state-of-the-art results across all metrics. Our method demonstrates a high success rate in completing individual tasks and consistently maintains strong performance when transitioning to long-horizon, multitask scenarios. Here we present qualitative comparisons between our proposed method and several baseline approaches in single-task scenarios. For the task of open the door, our agent naturally approaches the door, raises both arms, and uses both hands to push until the door opens steadily. In contrast, the agent from interface resorts to kicking the door and utilizing its entire body to open it forcibly. Although both methods successfully complete the task, our agent's behavior is more realistic and closely resembles human actions. For the task of sit on the chair, our agent naturally moves toward the chair, sits down comfortably, stands up smoothly, and subsequently. Conversely, the agent from UniHSI exhibits difficulty standing up, characterized by high-frequency jittering motions, resulting in an unrealistic and unnatural performance. Here we present qualitative results illustrating the performance of our proposed method within a long-horizon, multitask scenario, encompassing interactions with static, dynamic, and articulated objects.